Hello everyone, thank you for joining me today. Today our lesson is about optimization and minimization. So our objectives today are to solve optimization problems. Before we talk about the details, let's get an idea of what kind of problem we're talking about. So here's an example. The owners of a car rental company know that if they charge customers P dollars a day to rent a car, where P is between 50 and 200, the number of cars rented per day can be modeled by the linear function C of P equals 1000 minus 5P. So then, the revenue, the amount of money that the company brings in, would be represented by function R of P. And notice that function R is just C of P multiplied by P. C of P gives us the number of cars. We would take that number of cars and multiply by the number of dollars per car, P, in order to get the revenue. So we have this revenue equation, 1000P minus 5P squared. The question the owners might ask themselves is, what price should they set in order to maximize their revenue? After all, they want to make as much money as possible, so what price should they set? Set the price too high, not as many cars will be rented, they won't make as much money. Set the price too low, more cars might be rented, but each car is bringing in less money. So where's the sweet spot? What price should they set to maximize their revenue? Well, here's kind of the main idea behind our lesson today. If you consider this revenue function, notice that it's a quadratic function, right? And so just as a very rough sketch, that quadratic function is going to have a maximum at this local extreme value, right? And previously in this class, we've learned how to find those extreme values using analytic methods. Of course, we could just graph R and find the maximum that way, but without a calculator, we would use our first derivative test, our second derivative test, our candidates test maybe, if we have endpoints, which we do here, 50 and 200, to find what price they should set to maximize their revenue. So here's what we'll do. We will take this function R of P along with our endpoints here, which are 50 and 200. We'll put them in a table here because we do have endpoints to check. Remember, extreme values can happen at endpoints, but they can also happen at critical points. So let's find our critical points here by finding R prime. That'll be 1000 minus 10P. Critical points happen where that is undefined. Won't happen in this case. Critical points also happen where this is equal to 0, where the tangent line would be horizontal, slope of 0. Well, we take this equation, we solve it for P, we get P is equal to 100. So there's a critical point here where P equals 100. That's a possibility. So let's put it in our table and let's check these candidates now. We've got to plug 50 in here, we've got to plug 100 in here, we've got to plug 200 in here to find the revenue that each of those prices would earn per day. Well, I'm not going to show you that calculator work. The revenue when the company sets a price of $50 a day is $37,500. Plug in 100 to that function R, you get a revenue of $50,000. Plug in 200, a revenue of 0, too high of a price there. Okay. The candidate table makes it obvious for us here that the company should set a price of $100 in order to maximize their profit. Here's an optimization problem. It combines elements from previous lessons into a word problem type scenario like we see here. So let's talk general strategy here now. Of course, every problem might be a little bit different. We may be talking revenue. We may want to maximize the area, minimize the perimeter, maximize the volume of something. But here's a general strategy. Step number 1, draw a diagram and or define variables to model the scenario. Step number 2, write a function that represents what we are trying to maximize or minimize, and it may be necessary for us to make a substitution into that equation so that our equation is defined just on one variable. We'll see some examples of that. Once we have that equation, we'll identify our endpoints and critical points. Those are our candidates, remember, and then we will analyze those candidates, maybe using the first derivative test, maybe just using a candidate table to determine the maximum or minimum, whatever we're trying to find. Let's try this example where we are maximizing a product of two numbers. So find two positive numbers such that the sum of the first number squared and the second number is 54, and the product of those two numbers is a maximum. Doesn't really make a whole lot of sense to draw a picture here, but we can define our variables. So I'm going to have x and y be our two numbers here. Now we're trying to maximize the product. So I'm going to write this product equation over here, and the product of two numbers x and y is literally x times y. Now, the troublesome issue with that equation is that there's two variables here. We want to have our equation written in terms of just one variable. And that's where this secondary equation comes into play. The sum of the first number squared and the second number is 54. So the sum of the first number squared, I'm just going to pick x to be my first number. The sum of the first number squared and the second number, so the sum of x squared and y, is 54, equals 54. And what the secondary equation allows us to do now is to solve for y. Could theoretically solve for x, but easier to solve for y here, so that we can now make a substitution. We know that y equals 54 minus x squared, so let's go over here into our product equation, and before we differentiate to find critical points, let's make our substitution for y. Y is 54 minus x squared. And if we distribute our x, it'll make it easier for us to differentiate, so let's go ahead and do that. Now our primary equation, our product equation, the equation we're trying to maximize, is written in terms of just one variable, which will make differentiating a lot easier. So here goes. P prime would be equal to 54 minus 3x squared. P will have critical points wherever this is undefined, not going to happen for this quadratic derivative, or equal to 0. So let's now set this equal to 0 and try to isolate x here. I can add the 3x squared over and divide by 18, giving me x squared, divide by 3, giving me x squared equals 18. And now I can take the square root of both sides. And of course, I would typically have a plus or minus here, but we are told that these are two positive numbers, so only the positive root makes sense here. And I can simplify this radical down into 3 radical 2. There's a critical point. This is possibly one of our two numbers that will maximize the product. Now, do we have any endpoints explicitly given to us here? No. We're told that we're looking for two positive numbers, so our number has to be greater than 0. But other than that, we are not giving any specific endpoints to use. So let's just check this critical point here. In green now, off to the side, since it is our only critical point, we could probably assume that this is going to maximize the product, but let's double check that here, at least for this first example. Let's apply the first derivative test, and we could do the second derivative test here as well. But if I test points on either side of that critical point into the first derivative, p prime there, something bigger than 3 square root 2, maybe it's 10 or something like that. Well, if I plug in 10 here and evaluate, I'm going to get something that's negative. Something to the left of 3 square root 2 like 1, well, if I plug in 1 right here, I'm going to get a positive value for p prime. That tells us that p is increasing to the left of this critical point, decreasing to the right, and so we do in fact have a maximum there. We probably could have assumed that because we only had the one critical point, but we're covering all our bases here. So x is one of those numbers, 3 square root 2 is one of those numbers. To find the other, we're going to have to solve for y. Well, a couple different ways we could do that. We could use this equation here. So y is equal to 54 minus x squared, and I know what x squared is. It's 18. So then y is equal to 36. So the two numbers that meet the conditions and maximize the product of those two numbers are 3 square root 2 and 36. Wasn't a lot of context behind this problem, but it was a good one to get our momentum started for us to practice this process. Let's try another example that has a little bit more context. Find the length and width of a rectangle with area 48 square inches and minimizing the perimeter. Well, here it might make more sense to draw a diagram. So we've got some rectangle here. I'm going to call this distance x, this distance y, length and width. Find the length and width of a rectangle with area 48 square inches and minimum perimeter. So here we are trying to minimize the perimeter, and so I'm going to write our perimeter equation here, 2x plus 2y. That's how you would calculate the perimeter of such a rectangle. But now here again, we've got two variables. We want to have just one, so we need some secondary equation that will allow us to make a substitution, and this is it right here. The area of this rectangle is 48, so x times y equals 48, and now we could solve for either y or x, and then make our substitution. Here I'm choosing to solve for y. Y equals 48 over x. So let's make that substitution into our primary equation here. And do a little bit of simplifying before we go ahead and take our derivative. This would be what? 96 over x. We do not have any endpoints specifically given to us. Of course, our dimensions would be positive numbers, so anything greater than 0, I suppose. But we don't have a closed interval with endpoints to check for candidates, and so we'll just go with our critical points. So let's find those critical points, finding p prime and setting it equal to 0. Well, here our derivative of 2x is 2, and if you apply the power rule here, we will get a minus 96 over x squared. Let's now try to solve for x squared. In doing so, we're going to end up with a 2x squared on one side and a 96 on the other. So we can then divide by 2 and now take the square root of both sides. Normally, we would include the positive and negative root here, but we're talking dimensions, so only the positive root would make sense. And we could split 48 into 16 times 3, giving us 4 square roots of 3 for that x value. Now, to save a little bit of time in this video, I am not going to apply the first or second derivative test to actually test this and make sure it is the minimum. You're welcome to do so. You could also check with a calculator if you want to. I do want to find that other dimension y though, so switching colors. Once we know that x is equal to 4 square roots of 3, maybe I sub that in here to solve for y. So in purple now, y equals 48 divided by 4 square roots of 3. Well, that's going to be 12 over square root of 3. Rationalizing that gives 12 square root 3 over 3, which ends up being the exact same number as our x value. We get a square here. X and y are the same dimension to minimize this perimeter. Well, there's an example where we're minimizing perimeter. Let's try an example now where we're maximizing area. You have 200 feet of fencing to fence in a rectangular space in front of your house. See the diagram there. Notice that we don't need fencing alongside the house because the house is forming our border. So we need fencing around the 3 dotted sides in this diagram. What dimension should you use to maximize the fenced-in area? And what is the maximum fenced-in area? Well, we already have our diagram here, but let's label some of our sides. Pick any variables you want here. I'm going to use x's and y's. We are trying to maximize that rectangular area. So here our primary equation, area of rectangle is length times width. That has 2 variables in it. We want to get it down to 1. So we need some secondary equation, and that's where this comes into play. You have 200 feet of fencing to use, and notice we're going to have y feet plus x feet. We're not fencing in the side along the house because the house is taking care of that. So basically, if we take 2y plus x, that needs to equal the 200 feet of fencing that we have. So now we can solve for x or y. Here I'm going to solve for x. I think it's a little bit easier to do. X equals 200 minus 2y. So let's go over to our primary area equation here and make our substitution. X is 200 minus 2y, so we'll sub that in. Do a little bit of simplifying before we take our derivative to find critical points. We don't have explicit endpoints to test here. So let's set our derivative equal to 0 and solve. We could test that using the first derivative test, second derivative test, whatever. But since it's the only critical point we found, we're going to run with it here. So 50 is our dimension that runs perpendicular to the house. Let's find the dimension that runs parallel. So we got to solve for x now. So we can come back here and we can solve for x accordingly. X equals 200 minus 2 times y. That's 200 minus 100, which is 100. So our dimensions here in red are 50 feet by 100 feet, where the 100-foot side is parallel to the house. And we were asked to actually find the maximum area as well. Well, length times width, 50 times 100, 5,000. Pretty big, pretty big fenced-in area there. Now sometimes, especially if we're preparing for, an AP exam, perhaps, we may be asked to maximize area not so much with context to it, but rather on the coordinate plane using coordinates, like we're going to finish our lesson with here. So a rectangle has its two lower vertices on the x-axis and its two upper vertices on the semicircle given by the equation y below. So we've got some rectangle here such that we have one vertex here, here, and then the upper vertices fall on this semicircle. So here is some generic rectangle that is being described in this problem. It says what length and width will maximize the area of the rectangle. Well, let's give some names here. Let's call that y. Since we're working on the coordinate plane, I'm going to call this x, and based on the symmetry of this rectangle, this distance would be x as well. So please recognize that collectively then, this whole bottom side is 2x. So we are trying to maximize the area. So here comes our primary equation. Base times height, area of a rectangle there, 2x times y. Here again we have two variables where we only want to have one. Well, take a look. We can make a substitution. We know what y equals in terms of x. I'm going to scoot over a little bit here because we're going to need some room. You'll see why in a second. So area is 2x times y, but we know what y is equal to in terms of x. There it is. Here's a situation where when we go to find our derivative to get our critical points, we're going to need the product rule. And remember, we're going to be setting this derivative equal to 0 or finding where it's undefined. So here goes. I'm going to set it equal to 0 right away. Product rule says take the first times the derivative of the second. So here goes. We could recognize this as 16 minus x squared to the power of 1/2 maybe, right? Apply the power rule. 1/2 comes down in front. We subtract 1 to get the new exponent. And per the chain rule then, we got to multiply by the derivative of the inside, which would be negative 2x. So there is first times derivative of second. Now we're going to add the second times the derivative of the first. And the derivative of the first, 2x, would just be 2. Well, I'm going to rewrite this a little bit before we panic too much about solving for x. What are we going to end up with here? Well, this 2 can cancel with this 1/2, but we still have negative 2x squared on the top here. I'm going to move all of this stuff down to the denominator because it has a negative exponent, and I'm going to rewrite it as a square root to help myself out. Over here, there's not much I can do about rewriting this right now. Maybe I put it over 1 so that we have two fractions, I suppose. Well, critical points happen where this derivative is equal to 0 or undefined. Well, this derivative will be undefined for x equals 4 and negative 4. Okay, so it would appear that we have critical points there, but if we let x equal 4 or negative 4, then these endpoints are right here at the endpoints of this semicircle, and now we don't have any height to our rectangle at all. And so I would say that negative 4 and 4 are actually outside of the reasonable x values here. I would say we're looking at anything on the interior of that interval. Okay, so we're not going to get critical points that way, but let's set this equal to 0 and solve to find our critical points that way. And that might seem like it's going to be a headache, but let's see what happens. I'm going to take this negative fraction and I'm going to add it to the other side. That'll give us a 2x squared over a square root of 16 minus x squared, equaling this stuff over here, which was 2 square roots of 16 minus x squared over 1. Whether you recognize it or not, we have a proportion on our hands where we can solve by cross multiplying. 2x squared times 1 would equal this cross product here, and we have our 2, but if we take square root 16 minus x squared times square root 16 minus x squared, we're going to get 16 minus x squared, just like how square root 3 times square root 3 would give us just 3. Well, let's cross out the 2's. We now have x squared equals 16 minus x squared. Now we can get all the x squareds on the same side. Divide by 2. Take the square root to both sides. And the square root of 8 simplifies down to 2 square roots of 2. We would typically have a plus or minus there. The positive root would be here, I suppose. The negative root would be here, I suppose. Well, now that we have our distance for x, we got to figure out what y is, and we can use our equation here. So here goes, y is equal to the square root of 16 minus x squared. Now we knew that x squared was equal to 8. So y is equal to the square root of 16 minus 8. So again here we get square root 8, which is again 2 square roots 2. Now be careful, you might think that we have a square because we got the same thing for x and y, but remember, the bottom side of a rectangle was not just x, it was 2x. So for our dimensions here, if I want to draw, the rectangle again, for y we got 2 square roots 2, but this bottom side is 2 of those x's. So 2 square root 2 times 2, 4 square root 2. Here is the length and the width that will maximize the area of this rectangle. There we have it. We learned a little bit about optimization and minimization today. Thank you for watching.